So a binomial distribution is where we take a Bernoulli trial and we repeat it multiple times. So remember our Bernoulli trial, it might be flipping a coin or rolling a die. Well, instead of doing it just once, we're going to do it more than once. And what we do is we let the discrete random variable, x, count the number of successes. So the same way we did in a Bernoulli trial, but here we're not limited to only 0 or 1 success. If we did, say, 4 flips of a coin, then we could get anywhere between no successes and 4 successes. And the shorthand notation is just to say that our discrete random variable x is a binomial distribution n, p, where our n here is the number of trials, and our p here is the probability of a success on an individual trial. So this is going to be the same as your value for p for a Bernoulli distribution. So just looking at a coin, for example, if we flipped a coin 6 times and we counted a tail as a success, then our x would be modeled by a binomial distribution. 6 times we flip that coin, and the probability of success each time is 0.5. Let's take a look at a few examples. So down here, example 1, we roll a fair 6-sided die 4 times, and we count a success if we roll a 1 or a 5. And then we let the discrete random variable x denote the number of successes that are achieved. Now I'm going to come back to this part in a bit, and we're going to answer part A. So state the distribution of x. Well, x here would be a binomial distribution. The number of trials that we do is 4 trials, and the probability of success on an individual trial. So a success is counted if we get a 1 or a 5. So if we get 2 out of the possible 6 outcomes available to us. So 1 out of 3 would be our probability. So here our n is 4 and our p is 1/3. Now we're going to use these parts here to find the mean, the variance, and the standard deviation. So the expected value of x, or just the mean, which is mu, well, that's just n times p. So that's just 4 times 1/3, which is 4/3, which is just 1.333. The variance, being my sigma squared, well, that's this part here. That's my n times p, so that's my 4/3, which we just worked out, multiplied by 1 minus 1/3. And if you pop that into a calculator, you will get 0.8889. And then the standard deviation, or just sigma, that's equal to the square root of my variance, which is just 0.9428. So we've worked out the mean, the variance, and the standard deviation of our random variable x. Here we have to use this part. So for part C now, we need to find the probability that we achieve exactly 1 success. So we just follow this formula here. So the probability that x is equal to 1, so that we strictly get 1 success. So that is from n, so that our n is 4. Choose what we want our x to be, and we want 1 success. So from 4, choose 1, multiplied by our probability, which is 1/3, to the power of x, which is just 1, multiplied by 1 minus 1/3, which is 2/3, to the power of n minus x, so to the power of 4 minus 1. And if you pop that into a calculator, you will get 0.3951. So the probability that you succeed exactly 1 time out of the possible 4 is 0.3951. Now we need to find the probability that x is less than or equal to 1. And I'm just going to keep that formula up the top there, so we've got it handy. So for x to be less than or equal to 1, that's just the same as the probability that x is 0 plus the probability that x is 1. Now we've already worked this bit out, so we just need to work out the probability that x is 0 and then add them together. So following the same formula, the probability that x is 0, that is just equal to, well, from 4 choose 0 multiplied by my 1/3 to the power of 0 multiplied by 2/3. So that's your 1 minus a third, gives you your 2/3 to the power of n minus x. So 4 minus 0 is just 4. And your answer here is 0.1975. So the probability that x is less than or equal to 1 is just the probability that x is 0 plus the probability that x is 1. And well, we've worked out the probability that x is 0 now. We know that that's 0.1975. And the probability that x is 1, we work that out up here to be 0.3951. And if you add those together, you get 0.5926. Now, another way that you can calculate this, if you had a Casio ClassPad, for example, we use what we call a binomial PDF function. So in your Casio ClassPad, if you've got one, you should be able to go binomial PDF. Now, what's written in here is the number of successes that we want. So if we were to do part C again, we want exactly one success. So one success. And then the number of trials that we're doing, 4 trials, and the probability of success on each trial, 1/3. And if you pop that into a calculator, you should get this answer pop out again, so 0.3951. Likewise, if you were going to work this one out, the probability that x is 0, you would just do binomial PDF, and then 0 is the number of successes we want. We're doing 4 trials, and 1/3 is the probability of success on each trial. And if you pop that into your Casio ClassPad or just any online binomial PDF calculator, you should end up with 0.1975 as your answer. But what if I want to work out the probability that x is less than or equal to 1? Well, I would just add these two numbers together. Or alternatively, I can use something called a binomial CDF function. So we go binomial CDF. And we set our lower limit, so we can go anywhere between 0 and then our upper limit, 1. So 0 to 1. Or if we wanted to know the probability that x was less than or equal to 4, we would go from 0 to 4. But in this case, 0 to 1, and our number of trials, 4, and the probability of success on a trial being 1/3, we should get as 0.5926. So if you did a binomial PDF, and you want to work out the probability that you get exactly 1 success, then you would get this answer. If you wanted to know the probability that you get exactly 0 successes, you would put this in and you would get this answer. And you could add them together to give you this answer here. So this is a little bit of a shortcut when we're working with the less than or equal to's or greater than or equal to's. Hopefully that's made some sense. We're going to do a couple more examples and see if we can get the hang of it. So let's come over here. So here you roll 2 fair 6-sided dice 5 times. And we denote a success if we get doubles, so 2 of the same number. Let the discrete random variable x denote the number of successes achieved. So first of all, we need to state the distribution of x. Well, x is a binomial distribution. Now the number of trials that we do, 5 trials, and the probability of a success on each trial. So we succeed if we roll doubles. So if we got a 1 and a 1, a 2 and a 2, all the way down to a 6 and a 6, all of those are viable options for a success. Now there's 36 different possible outcomes you can get when you roll 2 die. So it would be 6 out of 36, which is just 1 in 6. So the probability just being 1 out of 6 is the probability of a success for us. Now the mean, so here I should just write quickly, n is 5 and p is a 6th, because that will help us when we're subbing into these equations. The mean, which is just this part here, so my expected value of x being my mean, that's just n times p, so 5 times a 6th. And if you pop that into a calculator, you just get 0.8333. The variance, so into this part here, we do our n times p, which we've already done. So that is our 5/6 multiplied by our 1 minus a 6th. And if you pop that into a calculator, you get 0.6944. And then our standard deviation, so just sigma, well, that's the square root of our variance, which again, if you pop into a calculator, you just get the same as the average, 0.8333. Okay, find the probability that we achieve exactly 5 successes. So the probability of a success is only 1 out of 6, so not very likely, and we need to do this 5 times in a row. So we're already thinking that our answer is going to be pretty small. So let's keep that in the back of our mind, because that's going to help us check whether what we get makes any sense. So the probability that x is 5, so we actually get 5 successes in a row. We put in our n, so we're looking in this formula now. The number of trials we do, 5 trials. The number of successes we want, also 5. The probability of a success is only a sixth to the power of the number of successes we want, which is our x, our 5, multiplied by 1 minus a sixth to the power of 5 minus 5. And if you pop this into a calculator, you'll get an answer of 0.000126. So incredibly small. Okay, you can try it. Get 2 dice, roll them, and see if you can get 5 doubles in a row. Pretty unlikely. The probability that x is less than or equal to 4. Well, given that we only do 5 trials, this is the same as the probability, this is the same as 1 minus the probability that x is 5. If you think you can either get 0 successes, 1 success, 2 success, 3 success, 4 successes, or 5 successes, the probability that x is less than or equal to 4 is just all of this space. So that's the same as 1 minus the probability of what's left over. And we've already calculated that. So if we pop this into here, then you're going to get an answer of 0.999871, which is far more likely. Alternatively, remember, if you have the binomial PDF calculator or a CDF calculator, whether it's on a ClassPad or a computer or something, if we wanted exactly 5 successes, then we say binomial PDF. Now we want exactly 5 successes. The number of trials we do is 5, and the probability of a success in each trial is 1/6, and that will yield us this number here. If I wanted this one here, I would just do binomial CDF, because now I'm accumulating across more than just the 1. It's less than or equal to. From 0 is the lowest I can go, to 4 is the highest I'm allowed to go, so less than or equal to 4. The number of trials I do is 5, and the probability of a success on each trial is 1/6. And if I popped that into my calculator, I would end up with this answer here. So that's another example of us using these binomial distributions. Let's have a look at a third and final example. So here we have 3 buckets, and in each bucket there are 10 balls. 6 of them are blue and the remaining are yellow. So there are 4 yellow balls in each bucket. We pick 1 ball out of each bucket and we let the discrete random variable x denote the number of yellow balls that we can collect. The distribution of x, well, it's a binomial distribution. Now, the number of trials that we do, there are 3 identical buckets and we're picking 1 ball from each bucket. So there are 3 trials there, 3 identical trials, each bucket collection being a trial. And the probability of a success in each trial, well, there are 4 yellow balls which we could succeed with out of a possible 10. So 4 out of 10, or just 0.4. So our n is 3 and our p is 0.4. The mean, the variance, and the standard deviation. So the mean, or the expected value of x, is just n times p. So 3 times 0.4, so I just get 1.2. The variance of x, being my sigma squared, that's just my n times my p, so my 1.2 multiplied by 1 minus 0.4. And if you pop that into a calculator, you just get 0.72. And then my standard deviation, just my sigma, well, that's the square root of 0.72, which just works out to be 0.8485. Now, the probability that we get exactly 3 yellow balls. So using this formula here, the probability that x is 3. Well, from 3 possible trials being my n value, my x that I want 3 successes, times the probability of a success, 0.4, to the power of 3, times 1 minus 0.4 to the power of 3 minus 3. And if you put all of this into a calculator, you just end up with 0.064, or just 6.4%. So quite a small probability that you manage to get exactly 3 yellow balls. Alternatively, I could use a binomial PDF calculator. The number of successes I want is 3. The number of trials I do is 3, and the probability of a success on each trial is 0.4. And if you put that into a binomial PDF calculator, you'll get the same answer. The probability that x is less than 2. So this is the same as the probability that x is 0 plus the probability that x is 1. We can't have 2. It has to be strictly less than 2. Now, if I put this, I could calculate it like I did this, and I could do both individually. But, who's got the time? So let's use a binomial CDF calculator, where we need to go from lowest we can have is 0, the highest we can have is 1, the number of trials we do is 3, and the probability of success on each trial is 0.4. And if we put this into a calculator, we end up with 0.648. Now, a stand at the fair offers you to play this game for $10. If you collect at least 2 yellow balls, then you get $20 back. Is it wise for us to play the game? Well, we need to work out the probability that we get at least 2 yellow balls. So the probability that x is greater than or equal to 2. Well, we can spot that this is just 1 minus the probability that x is strictly less than 2, which is 1 minus 0.648, which we calculated in the previous question, which is just 0.352. Now, if you didn't see that, it's okay. We can use the binomial CDF, and we can go from 2 to a maximum of 3 trials, probability of a success on each trial being 0.4, and you'll get the same answer. So it doesn't matter which way you do it. So now we have to think, is the probability of success being 0.352 worth putting $10 down for a $20 return? Well, let's think about the expected amount of money that we should make. So the expected amount of dollars, if you like, well, 0.648 of the time, so 64.8% of the time, we lose. We get less than 2 yellow balls. So when we lose $10. However, when we win, so 0.352 or 35.2% of the time when we win, we gain $10. So our expected amount of dollars that we should be expected to make over a long period of time here, if you put this into a calculator, is negative $2.96 per trial. So each time you play this game, you're expected to lose $2.96. So no, this would not be a good idea for us to play this game. You could also look at this and go, well, the probability of me winning is 0.352. And I'm getting a 1-to-2 payout, which is like a 50-50. So it's a lower probability than 50-50, which means it's definitely not worth me playing this game. So that's it for binomial distributions. Hopefully that's helped make some sense how we can do the mean, the variance, the standard deviation, and hopefully like the binomial PDFs and CDFs, and especially using this equation here and getting some practice making some sense of that.